Welcome to the deep dive. You've probably bumped into large language models, LLMs, maybe without even realizing it. We're talking about things like GPT-4, Llama, Qwen 2.5, these incredibly powerful engines. They're behind so much of modern AI, and they are dazzling, right? They can tackle complex math, write pretty sophisticated code, just impressive stuff right out of the box. They show this amazing zero-shot ability across tons of different areas. But, and this is the crucial bit, for all that power, real-world uses almost always need something specific, something tailored. You might need it to understand your company's internal jargon, maybe adopt a certain tone, or just work really well with a niche data set. So custom changes are pretty much always on the table. And while that customization can be surprisingly expensive and take a lot of time, think of it like buying a super high-performance race car. It's powerful, sure, but you still have to spend days tuning it for every single track. That tuning, that's the bottleneck.
That's a great analogy. Exactly. Yeah. And, that's why methods like parameter efficient fine-tuning, BEFT, sort of popped up, especially low-rank adaptation, which most people just call LoRA. It's become super common precisely because it cuts down those customization costs. How LoRA works, basically, is you insert just a small set of trainable weights, tiny, really, compared to the whole model, and you keep the vast majority of the original LLM frozen. So, yeah, much, much more efficient than retraining the whole beast from scratch.
Okay, so LoRA helps, but you mentioned a bottleneck still exists.
Yeah. Even with LoRA, there's still a pretty significant hurdle. The thing is, each new task or each new data set you want to adapt to still needs its own separate optimization run, its own training cycle. Let me give you a concrete example. Adapting even a, let's say, relatively small model like the 0.5 billion parameter Qwen 2.5, using LoRA, that can still tie up 4 powerful A100 GPUs for half a day. Now imagine trying to deploy specialized versions at scale, maybe hundreds of different users, tons of different data sets.
Yeah.
That per task training, it just becomes this massive computational barrier. Often it's just prohibitive.
Right. That scaling problem sounds like a major headache. So if that's the hurdle, how do we, get over it? Is there something new on the horizon?
There is, and that's exactly what we're diving into today. It's something genuinely groundbreaking, I think. It's called Drag-and-Drop LLMs, or D&D for short. And our mission, really, for this deep dive is to unpack how D&D just completely sidesteps that per-task training problem. It generates these specialized LLMs in seconds, literally seconds. And we want to explore what that means for, the whole future of AI customization.
Okay, drag-and-drop LLMs. That name itself is intriguing. Generating specialized models in seconds, bypassing training. That sounds almost too good to be true. It challenges some fundamental ideas, doesn't it? Like skipping gradient descent altogether.
It really does. It's a fascinating shift in thinking. The core insight behind D&D is actually, quite elegant when you break it down. A LoRA adapter, those small weights we add for specialization, it's essentially just a function of the data it was trained on, right? Gradient descent traditionally is what sort of drags the base model weights towards the best configuration for that specific task data. So the D&D idea is, what if we could learn that mapping directly, go straight from a description of the task, maybe just a few example prompts to the exact number of weights needed for it? Could we just, skip that whole slow, iterative gradient descent process?
Learn the mapping directly, so like predicting the outcome of the training process without actually doing the training.
Precisely. That's exactly what D&D does. They call it a prompt-conditioned hypergenerator. You can think of it as this clever system. You feed it just a few unlabeled prompts from your target task. These act like fingerprints, you see. And then, bam, in seconds, it directly outputs the complete set of LoRA adapters tailored for that task.
And the drag-and-drop name comes from that.
Yeah, it captures that feeling. It's intuitive, it's tuning-free, like dragging a file onto your system.
Yeah.
And it just works. No complex setup, no waiting for optimization runs, instant configuration.
Okay, walk us through the mechanics then. How does it actually do that conversion from prompts to weights?
Right, so internally, it starts with a lightweight text encoder that takes your batch of input prompts and distills them down into something called condition embeddings. These embeddings are basically compact numerical representations that capture the essence of the task described in those prompts.
Got it. So condense the task description. Then what?
Then those condition embeddings are fed into a special decoder. It's called a cascaded hyperconvolutional decoder. Think of this decoder as a specialized neural network designed specifically to transform those high-level task embeddings directly onto the full set of LoRA matrices, those small, crucial weights that adapt the main LLM. What it does, effectively, is it collapses the entire traditional loop data, leads to gradients. Gradients update weights. It collapses that into a single, super fast forward computation. No gradient descent needed.
Wow. That really is a fundamental shift. It's not just an optimization. It's a different way of thinking about specialization. It suggests that weights themselves, they can be treated almost like another type of data we can generate, conditioned on just a brief task description.
Exactly. You're generating the customization directly, not finding it through iteration.
So how does this D&D system learn to do that in the first place? How does it get this dragging ability, as you called it?
Right, good question. It learns this through a two-phase process. The first part is data preparation. What they do here is start by gathering a whole bunch of existing LoRA adapters, ones that have already been pre-trained on a wide variety of different data sets. They call these checkpoints.
Okay, so a library of successful customizations.
Yep. Then they randomly pair these checkpoints with batches of unlabeled prompts, just the input questions or instructions taken directly from the original data sets those LoRA were trained on. These prompts, remember, they act as those unique fingerprints for each data set, capturing what makes it distinct.
Okay, so you have pairs, prompts, and the corresponding ideal LoRA weights. What's the second phase?
Phase 2 is training the parameter generator. This is where the magic really happens. They use a pre-trained text encoder, something standard like sentence BERT, to take those batches of prompts and turn them into those dense embeddings we talked about.
The condition embeddings.
Exactly. Those embeddings then get fed into the D&D parameter generator, that hyperconvolutional decoder we mentioned. Now, this generator's job is to try and produce LoRA weights based only on those prompt embeddings. And it learns how to do this by comparing its generated weights to the original pre-trained LoRA weights from phase 1. They use a standard loss function, mean squared error or MSE, to measure the difference.
So it's learning to predict the target LoRA weights just by looking at the prompt embeddings. It learns the correlation.
Precisely. It learns the direct mapping. These kinds of prompts correspond to these kinds of LoRA weight adjustments.
Okay, that makes sense. So let's bring it back to the listener. If I have a brand new task, a data set this D&D system has never seen before, what do I actually do?
It becomes incredibly simple. For your new unseen data set, you just grab a few sample prompts from it. Doesn't even need labels or answers, just the prompts. You run those prompts through the lightweight text encoder to get the condition embeddings. Then you feed those embeddings into your pre-trained D&D generator. And almost instantly, it spits out a set of LoRA parameters tailored specifically for your new task. That's it.
No fine-tuning, no long optimization runs.
Nope. None. It's a zero-shot generation of the adapter. And this zero-shot capability is key. They tested it rigorously, both on tasks similar to its training data, like common sense to common sense, but also, impressively, on cross-domain tasks.
Cross-domain? Like what?
Like training the generator primarily on common sense reasoning tasks, and then testing its ability to generate LoRA weights for complex science questions. And it works surprisingly well.
Okay, this sounds revolutionary, but we need to talk results. How well does it actually perform? You mentioned speed, but what about the quality of these generated models?
The performance results are, frankly, jaw-dropping across a whole range of benchmarks.
Lay some numbers on us.
Okay, efficiency first. Compared to full fine-tuning, D&D achieves up to 12,000 times lower overhead. Let that sink in. 12,000 times.
That's astronomical.
It really is. It changes the game entirely. It's also about 2,500 times faster than even what they call mildly tuned full-shot fine-tuning, generating a single model. It's often a fraction of a second. For instance, creating a common-sense model adapter on one NVIDIA A100 GPU takes about 0.11 seconds.
Under a tenth of a second?
Yep. Even for bigger 7 billion parameter models on tough tasks like coding, it's typically under a second. Say 0.73 seconds for a 7B coding model adapter.
Okay, speed is undeniable, but speed isn't everything if the quality isn't there. How good are these instant models?
That's the kicker. The performance is often superior to traditionally trained LoRAs. On average, across diverse tasks, D&D yields performance gains of up to 30% over the strongest baseline LoRAs when tested on unseen datasets.
Wait, 30% better than a LoRA that was actually trained on that type of data?
Better than the average performance of LoRAs trained on similar tasks when evaluated on a new held-out task, yes. It generalizes incredibly well. And that zero-shot generalization we mentioned, it's robust. It really can adapt models effectively to completely new domains going from common sense to science, for example, without ever having seen data or labels from that new domain during its own training phase.
Can you give some specific examples like accuracy numbers?
Absolutely. So on common sense reasoning, using a benchmark called ARC-EASY, the baseline trained LoRAs averaged around 37.5% accuracy. D&D jumped that to 68.6%.
A huge jump. What about coding?
For coding, on Human Evil Pass at 1, the baseline was about 17.6%. D&D hit 32.7%.
Doubled it almost. Math.
Using the GSMAK benchmark.
Mm.
The baseline LoRa's got around 42.9% accuracy. D&D achieved 66.3%.
Consistently big games. And the cross-domain example, common sense to science.
Right. Adapting a model trained mainly on common sense to a science Q&A dataset. The baseline LoRa method got about 35.6% accuracy. D&D pushed that up to 45.3%. Still a solid improvement, even across domains. And importantly, this isn't just for small models. D&D scales well. It transfers effectively from the smaller 0.5 billion parameter models up to 7 billion parameter ones, maintaining strong performance even on really tough coding benchmarks like Live Code Bench. And consistently, these D&D generated models outperform the original Foundation LLMs too.
Those numbers are genuinely impressive. It's fast and high performing. What did the researchers find out about why it works so well? What makes it so robust? Were there specific experiments, maybe ablations, that gave some insights?
Yes, exactly. They did extensive ablation studies, basically, taking pieces away or changing things to see what matters most. And a few key things stood out. One was about the power of prompt. It turns out using just the pure unlabeled prompts as the input condition works best.
Just the questions or instructions?
Right. Surprisingly, adding the answers alongside the prompts, especially simple answers like ABCD choices you see in common sense tasks, can actually hurt performance.
Why would answers hurt?
The thinking is that those simple repetitive answers limit the diversity of the dataset fingerprint. They make different datasets look too similar in the embedding space, making it harder for the generator to learn the specific nuances needed for each one. Now, they did find that complex answers, like the detailed solutions in math problems, can work as conditions. But generally, just using the prompts is preferred, not least because prompts are shorter and more efficient to process.
Interesting. What else?
Another critical factor is diversity in the training data used to train the D&D generator itself. The more varied the data sets and LoRa checkpoints it learns from initially, the better it gets. More diversity means it learns a wider range of those condition parameter correlations.
So it sees more examples of how different types of prompts relate to different types of weight changes.
Exactly. And that leads to better generalization and higher performance boosts when it encounters completely new data later on. They also found that randomly selecting batches of prompts during the D&D training, they called the strategy 2, was much better than using a fixed set of prompts for each checkpoint. Randomness exposes it to more diverse condition parameter mappings.
Okay, diverse training data using just prompts. Anything else major?
Well, they also compare D&D directly to other common adaptation methods like few-shot tuning or in-context learning, ICL, where you give the model a few examples in the prompt. D&D significantly outperformed both of those, especially when only a small number of examples or shots were available. And critically, D&D does this with negligible overhead and without needing the answers for those examples, unlike few-shot or ICL.
Right, because it only needs the prompts as input. That really hammers home the drag-and-drop idea. It sounds incredibly practical. The research, I believe, even had visualizations showing how the generated parameters compare.
Yes, they did. Visualizations showing that the LoRA parameters generated by D&D are not only landing in the right neighborhood in the high-dimensional weight space, close to where traditional fine-tuning would end up, but they often achieve even better performance metrics.
So let's wrap this up. What's the big picture here? What does this D&D breakthrough really mean? It feels like this ability to just take unlabeled prompts and instantly generate highly specialized LoRA weights. It's more than just faster tuning. It feels like a paradigm shift in customizing LLMs. It really lowers the barrier, making it possible to rapidly tailor these powerful AI models to very specific needs without that huge computational cost we talked about earlier.
I agree. I think the underlying concept itself is profoundly interesting. This idea that neural network weights aren't just something you painstakingly find through optimization, but something you can directly synthesize. Treat them as a new kind of data modality you can generate, conditioned on something as simple as a prompt. It really does open up a fascinating new direction, not just for LLMs, but potentially for vision language models, maybe other complex AI systems too. Customization becomes much more dynamic, much more on demand.
So here's a final thought to leave you with. If we truly can generate the precise modifications an LLM needs, essentially on the fly, just based on a few examples of a new task, what does that unlock? What kinds of new applications or maybe deeply personalized AI experiences become feasible when the friction of adaptation practically disappears? How might this fundamental change in how models are adapted reshape our entire interaction with AI, making it truly bespoke, instantly responsive, no matter what new challenge you throw at it?